So welcome to the next video lesson in the acids and bases series. Now we have to calculate the pH of these buffers. If you remember, the previous lesson was a qualitative look at how buffers were made and how their pH remained almost constant when you added acids or bases to them, at least small amounts of acids and bases. Now what we have to do is we have to calculate the pH of these buffer solutions, and luckily we only have to do acidic buffers. So let's go straight into an example question. The buffer questions, buffer calculations tend to look a bit complicated and scary, but actually they're not as scary as they look. You'll soon get the hang of them, and they all follow a very similar pattern. So here we have a buffer solution containing 0.4 moles per decimeter cubed of methanoic acid. That's our weak acid. And it also contains 0.600 moles per decimeter cubed of sodium methanoate. That's the salt of the acid. And we're given the Ka, the dissociation constant of the acid, to be 1.6 times 10 to the minus 4 moles per decimeter cubed. And the question is asking us what the pH is of this buffer. So the first thing we do is we are going to write down the equilibrium equation, and we've got methanoic acid. So as you know, that's HCOOH, and that dissociates slightly, very slightly, to hydrogen ions, and methanoate ions. And it's a weak acid, so most of the acid particles remain undissociated. And the reason we write this equilibrium equation down is so that we can write an expression for the acid dissociation constant, which we are given the value of in the question. So Ka, you'll remember, is the concentration of the products divided by the concentration of the reactant to the power of the moles in the balanced equation. So one of the products is hydrogen ions, so we're going to write that on the numerator, and that's multiplied by the concentration of the methanoate ion. And they're both to the power of 1 because there's 1 mole of each in the balanced equation. And on the bottom we have the acid concentration. So then we have the acid concentration. We have the expression like that, and the next step for us to do is actually to rearrange this equation, the acid dissociation constant equation, because what we're really after is the hydrogen ion concentration. So let's multiply both sides by the acid concentration, and then divide both sides by the ethanoate ion concentration, and what we'll end up with is the hydrogen ion concentration equal to dissociation constant times the acid concentration all divided by the ethanoate ion concentration. So now we have an expression for the hydrogen ion concentration, and as we did before, as soon as we get that, it's easy to calculate the pH. So let's have a look and see what we've got. In the question we're given the acid dissociation constant, that's good, and what we need then is the acid concentration and at equilibrium, that is, and the ethanoate and the methanoate ion concentration at equilibrium. So in order to get these, we need to make two assumptions. Right, so I'm going to write the assumptions in green, let's say. Okay, assumption number 1 is about the acid concentration. Now it's a weak acid, it's methanoic acid. It's a weak acid, so the assumption we're going to make is that the concentration at equilibrium is equal to the concentration at the start because it's so weakly dissociated. And we're actually given the concentration at the start, so what we're going to assume is that at equilibrium we have 0.4 moles per decimeter cubed of the methanoic acid. So I'm going to write that assumption down now. So the equilibrium concentration of methanoic acid is the same as starting concentration That's this assumption we're going to make because it's so weakly dissociated. Okay, and the second assumption we're going to make is about the methanoid ion concentration on the numerator. So that's assumption number one for the acid concentration, assumption number two for the methanoid ion concentration. Now, this is fully dissociated. So at equilibrium, we're going to assume that the methanoid ion concentration is the same as the starting concentration of sodium methanoate, because all of the sodium methanoate particles have dissociated, and so at equilibrium the concentration of the methanoid ions is the same as the concentration of the sodium methanoate at the start. So I'll write that down longhand as well. Equilibrium concentration of methanoate is the same as the starting concentration of sodium methanoate. And then we can make that assumption because it's fully dissociated. So if we make those two assumptions, then we have all of the values that we need to find the hydrogen ion concentration. So then let's just feed the values in. So Ka we're given in the question, 1.6 times 10 to the minus 4. And the acid concentration is 0.4 moles per decimeter cubed. And the methanoate ion concentration is 0.6. And when we feed that into our calculator, we're going to get 1.07 times 10 to the minus 4, and its concentration, so we've got moles per decimeters cubed. And that's the tricky bit, because you remember converting from hydrogen ion concentration to pH, it's quite easy. We just go back to our pH equation. pH is the minus log of the hydrogen ion concentration, if you remember. And so that is just the minus log of 1.07 times 10 to the minus 4. And that comes out at 3.97. And that's what the question is asking us for. You'll remember that the first way to make acidic buffers was to take a weak acid, say methanoic acid, and mix it with the salt of that acid, say sodium methanoate. And that would give you a concentration rich in methanoate ions and methanoic acid ions. So that was the original way of making acidic buffers. The other way that you need to know that we can make acidic buffers is just by going back one step. So let's use the same compounds. Let's use methanoic acid. So we'll just write the equilibrium equation down for that. So we've got methanoic acid, and that's in equilibrium with its dissociated hydrogen ions and the methanoate ions. Okay, so we've got that, and that's the same as before. But instead of adding the salt of the sodium methanoate, the salt of the acid, what we're going to do is we're going to add a strong base, for example, sodium hydroxide. So if we add sodium hydroxide instead, what's going to happen is that the sodium hydroxide is going to react with the acid particles. So in this case, that's methanoic acid. So you've got COOH plus the sodium hydroxide. And that's not an equilibrium reaction, that is a full reaction. So you're going to get sodium methanoate write it like this, and a water particle, the salt and the water particle. And so you see what we've done is we've ended up with the same sodium methanoate salt as we had in the earlier example. And of course we've started off with excess acid particles, so we've still got a lot of acid particles in the equilibrium mixture. So we ended up in the same place, but we've just started one step earlier. So we've sort of made our salt as part of the buffer reactions. So just to recap, in this way we're going to start off with our methanoic acid as before. So we're going to, and that's only very slightly dissociated, so that we've got lots of acid particles, methanoic acid particles in the equilibrium mixture. And by adding the sodium hydroxide, that's reacted with some of the acid particles to make these sodium methanoate ions. So in the equilibrium mixture we have the same as before. We have the sodium methanoate ions, lots of methanoate ions, because they're the important part of the buffer, and we've got lots of methanoic acid particles still left, because we've not reacted all of them, because we only added a small amount of sodium hydroxide. Okay, the best way to understand this is to look at a worked example. Okay, and we have one. So we have a buffer being formed by mixing 15 cm cubed of our strong alkali, that's 0.1 mole per dm cubed of sodium hydroxide, and we're mixing that with the weak acid. So we've got 30 cm cubed of 0.6 mole per dm cubed of propanoic acid, and the question wants us to calculate the pH of this buffer solution. So in this second type of buffer calculation, what we need to do is first consider the neutralization reaction that's happening. Okay, so we've got an acid and a base in a neutralization reaction. And let's just write the balanced equation down for that neutralization reaction. So our acid is our propanoic acid, and we've got CH3, CH2, COOH, that's our acid, and we're reacting it with our base, which is our sodium hydroxide. And that's not an equilibrium reaction, that's a neutralization reaction going to completion, and that's going to form our salt, sodium propanoate. With our propanoate ion and our sodium ion, and of course we get a water molecule being thrown off as well. Okay, so that's our neutralization reaction, and the first thing we want to do after that is to work out the moles, first before neutralization and then after neutralization. Okay, so I think a way that is going to help you make sense of this is to consider the three compounds that are involved. So we'll have a table with propanoic acid, and we want some sodium hydroxide, and we also want some sodium propanoate. Okay, so, and we want the moles at the start of the neutralization, and we also want the moles after neutralization. And if we put that in a little table and build it up, then you'll see the logic of it as we go along. Okay, so I think that'll do. Let's say, so first of all, we want to work out the moles of propanoic acid before. So you'll remember that moles equals concentration times volume. And in this case, we are given the concentration at the start of the propanoic acid, which is 0.6 mole per dm cubed. And the volume, we're given 30 cm cubed, but of course concentration needs to be in decimeters cubed, so we'll just do 30 over 1,000 to put it into decimeters cubed. And so that is going to come out at 0.018 moles. That's the number of moles of propanoic acid we have at the start of the neutralization, before the neutralization reaction. And so now let's consider the sodium hydroxide. Okay, so same equation. So the moles are going to be the concentration times the volume, and the concentration in this case is 0.1 from the question, moles per decimeter cubed, and the volume is 15 cm cubed. All right, and in dm cubed, that is 15 divided by 1,000. So the moles of sodium hydroxide is going to come out at 0.0015 moles of sodium hydroxide before you start your neutralization reaction. Right, now before the neutralization reaction we haven't got any salt, so we can just put a fat 0 in there. All right, and to start with, what I would like you to do before we go and work out the moles after neutralization is just to notice that we have, by design, a lot more of the propanoic acid so it's more than 100 times, more than 10 times as much propanoic acid than sodium hydroxide, and that's by design because you don't want to use up all your propanoic acid. Okay, so now we can consider the situation after neutralization. So after neutralization, what we can see is that the moles of propanoic acid is going to be the moles that you started with minus the moles that have reacted with the sodium hydroxide. Right, and so the number of moles that have reacted with the sodium hydroxide is 0.0015, this number here. So let's just write that in. So the moles of the propanoic acid is going to work out to be 0.0165 moles. So you can see that from the balanced equation, it's a one-to-one relationship between the propanoic acid. Let's just write that in just to be clear. So it's a 1-to-1 relationship with propanoic acid and sodium hydroxide. Right, so for every 0.0015 moles of sodium hydroxide that's reacting with propanoic acid, that explains the fact that you're going to get 0.018 take away 0.0015, and that works out to be 0.0165 moles of propanoic acid after the reaction. That's what's left. Okay, so moving on to sodium hydroxide after neutralization. Now all of that has reacted. So all of the sodium hydroxide has reacted. So we're going to have a fat 0 left after neutralization. Now let's look back at the balanced equation, and we see that for every 1 mole of sodium hydroxide that reacts, we are also going to get 1 mole of salt that's produced. Okay, so if we've reacted 0.0015 moles of sodium hydroxide, that is the number of moles of sodium propanoate that we're going to get after neutralization. So we can write in here moles equals 0.0015, and that completes our table. Okay, so now we're sort of at the starting point of the previous calculation. So we've made our salt, we've made our salt that makes up our buffer solution, and now what we want to do is we want to consider the equilibrium equation, as we did before in the previous example. So our equilibrium equation is, of course, our acid, propanoic acid, and that's going to dissociate into a hydrogen ion and a propanoate ion. And in the equation, of course, we are given our acid dissociation constant here. So let's write out our expression for the acid dissociation constant. And you'll remember that it is the concentrations of the products to the power of the moles in the balanced equation divided by the concentration of the reactant, which is the propanoic acid. Now, why have we done that? The reason we've done that is because the question is asking us for the pH, and in order to calculate the pH, we need the hydrogen ion concentration. And the hydrogen ion concentration is going to come from the acid dissociation expression. So what we can do is we can take that, and as we did before, we can rearrange that for hydrogen ion concentration. So the hydrogen ion concentration is going to be equal to Ka times the concentration of the acid divided by the concentration of the propanoate. Okay, so good so far. And let's just have a look at this expression and see what we've got and what we haven't got. So that's what we want to find, the hydrogen ion concentration. That's what we want to find. We have our value of Ka from the question, 1.35 times 10 to the minus 5. All right, but do we have the acid concentration? And we're going to have to work that out. We've got the moles, but we don't have the concentration. And do we have the propanoate concentration? Well, we have the moles, but we don't have the concentration. So let's just work out those two concentrations here. So concentration is moles over volume. So if we're dealing with the acid, we've got 0.0165. And the volume, now notice the volume, you've mixed two solutions. You've mixed 15 of one and 30 of the other. So the volume is going to be 45 cm cubed. But it's 45 over 1,000 because we're always dealing with decimeters cubed. Okay, so that sum we'll put into our calculators in a minute. Let's do this one first. So we've got the moles of the propanoate. We worked that out as 0.0015. And that's all in the same reaction mixture. So the volume is also 45. And it's also 45 decimeters cubed. Okay, so let's work out those two numbers. And for the acid, that works out at 0.37. 0.37, and for the propanoate, that works out at 0.033. So when we feed those values into the expression for the hydrogen ion concentration, we've got Ka is 1.35 times 10 to the minus 5, and we've got these two concentrations. Now, then the concentration of hydrogen ions comes out at 1.51 times 10 to the minus 4 moles per decimeter cubed. Good, so we're nearly done. And the last step is just to use the pH equation. So let me just, instead of starting a new slide, let me just do it in this little bit of the slide here. So you'll remember that pH equals minus log of the hydrogen ion concentration. Hydrogen ion concentration we've just worked out at 1.51 times 10 to the minus 4, and so the pH is going to work out at 3.82, and that's the answer to the question. As usual, let's just check we've covered off our learning objective, which was of course to be able to calculate the pH of acidic buffer solutions. So let's just remind us, method 1 was when we started off with just the weak acid and the salt, and we used the expression for Ka to find hydrogen ion concentration, and then from the hydrogen ion concentration we got a pH. Quite simple. And then the second type of problem that we did involved a neutralization reaction first. Before we were able to use our Ka to get our hydrogen ion concentration, which then enabled us to get our pH. So we did those two types of questions, and hopefully they were clear, and I'll see you in the next lesson.